Alright, so we'll start with question 1 on this exam to review, and so we'll look at the naming. And so if you notice here that there are actually, at this point, 7 carbons. So that means that our parent for this is going to actually be the alkane chain. Right, so the benzene here is actually going to be named as a substituent. And so when we name benzene as a substituent, it is named as a phenyl group. So we're going to start numbering here, and we're going to number at the right side and go from right to left. And this is because if you look, I do have substitution either way I go, from left or right, at the second position, but I have another one that's closer on the right side. So I need to start numbering then from the right so that I end up with a lower total number of substituents there. So when I do this, I looked at this chain and I see that at 2 and 3 I have 2 methyl groups. So I'm going to add dimethyl to that. And of course, I need to make sure that I add both locants there to have the positions stated. So now I have 2,3-dimethyl, and then now I'm going to add the phenyl group, which is on 6. So 6-phenyl, and then this is going to be 7 carbons, so it's a heptane. All right, so now when we look at the other one here, we see that I have substituents that are equidistant from each other around the ring. So in order to know which way I need to go, I want to start alphabetically. So that means that bromine here, because it's a B, is going to be position number 1. And then I have to decide, do I go to the left or do I go to the right? And so if I look to the left, I see that I have ethyl. And if I look at the right, I see that I have a propyl group. So E comes before P. So I'm going to start numbering at the bromine and go to the left so that I would have a 3 on the ethyl group. So 1, 2, and 3 here. And then propyl is going to be number 5. So now you just need to list everything alphabetically and add it all in to make your name. So here I have 1 bromo, and then 3 ethyl, and 5 propyl, and then finally the parent here is benzene, so I need to add propylbenzene to that. Alright, so for this next one, we see that I have 2 groups that are adjacent to each other, so I need to get the overall lowest number, so I'm going to actually here start again with the chlorine and number down, and then going over to the ethyl group. So chlorine would be position number 1, and then nitro would be position number 2. So the other thing that I need to look at on this is I need to make sure that I list them alphabetically. So notice that ethyl comes before En. So if you see I put 2 nitro down, that would be incorrect. So let me erase that. And I actually need to put 4 ethyl here. Then do 2 nitro, so that everything is listed alphabetically. And of course I'm going to add benzene, which is my parent. Alright, so now let's look at the last one. Down here at the bottom. And this one is sort of one that looks a bit challenging, but it's really not too bad. So what we want to do is, of course, number again to get the lowest overall number. And the first thing I like to do in this case is I like to start making sure I name all of the individual pieces that are on the ring. So I'm going to start over there at the left and go over here and name this guy. So this is a sec-butyl group. And remember that the sec part we're not going to alphabetize that. This is the propyl, of course, and then down here is the isobutyl group, and then of course I have ethyl here. So now I'm just basically going to number where I have start there, and I'm going to number to give me the lowest overall number, and so we're going to list them again alphabetically. So if I put the sec-butyl there first, it starts with a B, so we don't count the sec part for our alphabetization. So I have here 1 sec-butyl. And then the next one that is going to come up alphabetically here is the ethyl. So I'm going to put 5 ethyl. And then 3 isobutyl. That does count. And then finally 2 propyl. And then add benzene as your parent name. And we've made it through the naming. All right, so in this one, we're looking at whether it's aromatic, anti-aromatic, or non-aromatic. And right off the bat, I noticed that this guy right here fits all the requirements for aromaticity, but it lacks the right number of electrons, so it is anti-aromatic. This guy looks to lack the electrons. So we have 4 pi electrons, 2 on each side. But then what we see is the lone pair. And the lone pair is actually going to be placed into a p orbital. And it's going to contribute to our aromaticity. And it's actually going to be sp2 hybridized. So now I have 6 total pi electrons that are used here. And so this one here is aromatic. The next one I have, again, I have 4 pi electrons. It fits all the rules except for the electron count. And so this one would be anti-aromatic. And then this one, I have 2 pi electrons that are in the ring there where I just marked. And then I have these other 2 pi electrons that are on the nitrogen. So this is going to contribute towards aromaticity. It's actually going to place those lone pair into a p orbital. And then I'm going to get the remainder of electrons. Remember that that's just one resonance structure there. I also have pi electrons that are going to count towards aromaticity here. So I have, in this case, a total of 6. And so this one gives me aromatic. This one actually also has all of the right criteria. Has the correct number of electrons, and it is therefore aromatic. And then finally, this one with the radical. This is one of the ones that we did in class. And notice that we said anything really pretty much that doesn't fit the 4n plus 2 pi electrons. This one then has 5. Then basically what we said is if it doesn't fit Huckel's rule, then we're going to go ahead and say that this one is anti-aromatic because we have 5 pi electrons here. So we have, again, everything met but the wrong number of electrons. This one, likewise, wrong number of electrons. We only have 4 pi electrons, so this guy is anti-aromatic. And then here comes this one. So I don't have these electrons that are available for the aromatic ring that are attached to the oxygen, so this one will be anti-aromatic as well. All right, so now...
Please go away. Let me sleep for the love of God!
If we look at this guy, we're determining whether or not something is basic, and we also need to look at the hybridization. So notice that I have p orbitals that are within the system that are attached to my nitrogen. So the lone pair on the nitrogen there is actually going to be perpendicular to the pi system. So you can see that I put this here with my p orbital, and then the sp2 orbital that is out to the left, that actually contains that lone pair. So it turns out that since that is perpendicular to my pi system here, that basically that means it's not counting. Counting towards it. Let me fix this here really quickly. So we have our pi system that's going all the way around, and it's not counting the lone pair within it to be aromatic. So this nitrogen is in fact basic with its lone pairs perpendicular to the pi system. So now we can move to the one here to the right of it, and we see that this one has, if we look, 4 different groups, bonding groups, and so we want to count, in this case, the lone pair it's occupying space. So if we look at hybridization here, then this one has to be sp3. And there's nothing holding back those lone pairs, so it is, of course, basic. Now we come to the one in the bottom, and we see, just like the example with the aromaticity, that this lone pair is actually going to be in a p orbital, and it's actually going to rehybridize itself to sp2. Because remember, we don't actually have any p orbitals in sp3. So in order for that to be the case, it must be sp2. So we have sp2 here, and since those lone pairs are actually not available for use as a base, as they're contributing to the aromaticity of that. So just make a note here that this one contributes here to our aromatic system. All right, moving to this one, we see that this one has 4 groups, counting the lone pair. So this one is in fact sp3, but the big problem is that that lone pair is actually tied up in resonance with the ring. So you could potentially draw a resonance structure there. It has a lone pair kicking in on that nitrogen. So just like so, right? So this one is basically going to be all tied up and not quite available for use as a base. So we have sp3 and non-basic. This one, again, here that we're looking at, we have those lone pairs that are, again, pushed into a p orbital. So it's going to rehybridize here to sp3, or sp2, excuse me. And we see that this one is non-available for use as a base. This one has lone pairs that are contributing to aromaticity. Then finally, we have our last example, which you can see that these lone pairs are in an sp2 orbital perpendicular again to the pi system, and so this one is available for use as a base. All right. So the key to question number 4 on the exam was to sort of evaluate carbocation stability, right? So when it says differing reactivity towards salicylic with water, that means actually forming the carbocation here and getting to this positive charge that we see. And so if I look at this carbocation, what I notice is that this one is just a secondary carbocation. And so remember that if we were looking at whether or not a carbocation will form, it is how stable is that carbocation. So I'll just draw the representative carbocations here above each structure, and then we can evaluate them. So this one is just secondary. This one is also a secondary carbocation, but it is secondary allylic. So that adds some resonance stabilization. This carbocation, however, is a bit different because notice now that everything is sp2, and this actually makes this something to be anti-aromatic. And so that's going to be highly unstable and unlikely to form. The last one, however, if I do draw the positive charge in there with all of the other electrons, I fit all the requirements for aromaticity, and therefore I have the right number of electrons, so it is aromatic. And so it makes it highly likely for that to form because it's very stable. So after we have sort of evaluated stabilities, we can now put these in sort of an order. So the one that is more likely to form and therefore most reactive, because we're looking again at whether or not it's likely to generate the carbocation, we can start with D because that one's aromatic. So it's highly likely to form, probably will happen fairly fast. The next one then is our one that has allylic stabilization, then our secondary carbocation, and then finally the one that's anti-aromatic, which pretty much won't want to form at all. Okay, so now we're going to move into the next question, which is Diels-Alder reactions. And so for these problems, what you want to do is you want to look for the double bonds that you see in the product. All right, so look for the alkenes. So remember, we need to get to something that looks like this. And so all we got to do is basically just attach all the different pieces that are there. So notice I'm looking for this sort of alkene that we have here. So when I go to the first one, I see that I have this alkene that's right there. So if I just kind of erase it and I put the diene next to it, and then you can kind of mentally erase the other, you can see that I have the dienophile. So we're going to label this as a phenyl with a pH so I can fit it in the box here. And again, start by this and then just add your pieces to it. The next one that I'm going to do is, of course, I'm going to place the double bond right in the center of that. And so there I have my dienophile. In this case, I'm going to do the same thing. I'm just going to put these guys back. And if I erase magically the other, I see that I have two of the same things here. So basically, I have a ring that has two double bonds. And I've got the same thing on either side. So I've got two of these dienes. And then I have one symmetric dienophile. Now, going down here to this guy on the bottom, what I notice is that if I do the same thing, I generate the same diene. But I do notice something a bit different here about this. So here's the diene that I have. But notice that I still have a double bond that is in the product. If you look above, there is no double bond that's in the product from the dienophile. So we have to have something there to allow us to keep that double bond, and what that is going to be our alkyne that we're going to use. Also remember when you're drawing the alkynes that they have a 180-degree bond angle. So you need to draw them where they're not bent. They have to be straight, just like this. Okay, so we go to the last one, and this one's asking you to determine the product. And so we just want to look for our diene. And so if I take this guy and sort of rotate it around so that I get to the S-cis conformation, you can see there that I have my diene. And so notice that we're going to form this 6-membered ring, and I'm going to put those pieces there from my diene, and then just add the phenyl there at the end.
Okay, so that's how it's gonna be.
In
Y'all wanna
these
play?
problems like this, these are ones that you just have to know your reagents. And so if I'm looking at this here, we see that it would generate a primary carbocation, which is pretty highly unstable and unlikely to form. And so therefore we're going to immediately get some rearrangement. So we could have something like a hydride shift that would come over and allow us to form the secondary carbocation, which is more stable. So thus we have our product that has the this rearranged compound here on it. Now the other thing is we got to look at our activity and directionality of what's on the ring. And so we see that the strongest director that we have is the methoxy group. It directs ortho and para, so it's likely going to want to go ortho and para to it. So here we have now our rearranged product there. Okay, so potassium permanganate, when we react this with something that has CHs that are adjacent to an aromatic ring, remember that something very special happens. If there is any CH that's there, this will actually oxidize it all the way to the carboxylic acid. All right, so now I've finally got that written. So what we want to do is look over here, and we see that we have a CH there, I have a CH here, and then of course I have these CH3s that of course have CHs on the end. So everything is going to get over-oxidized all the way to the carboxylic acid. Running out of room. So we should have 4 carboxylic acids on each piece. All right, so the next one that we're looking at is simply an acylation reaction, but it was taken just a little step further in that it's going to add just like you would normally expect something to add with an acyl group. We're going to, of course, form the oxonium ion, but then we have another acyl group that's already on there, so it can add again, and it forms a ring for us. So here's after the first addition, but I still have the acyl chloride left over. So I've got more AlCl3 in there because it's a catalyst, it got regenerated, and then I'm actually going to add it again. And then this last one is just going to be a Friedel-Crafts alkylation, but what we want to do is we want to look at our sort of directing effects, and so we can see that we have a hydroxy on there, and so hydroxy is a very strong activator. So that's going to be our director for this reaction, and it's going to direct ortho and para. And so the only logical place to put the new methyl group is to the left of it. The para position is blocked with the bromine. And this would be your major product. Now, we're going to look here at the top, and I see that I have a nucleophilic aromatic substitution reaction, and I know that for 2 reasons. Number 1, my ring is incredibly electron deficient, and I have a strong nucleophile. So I'm simply going to substitute the chlorine with this nitrile group here. And there is your product there for this guy. The last one, notice that with AlCl3 it doesn't work with the nitrogen, so we get no reaction. Okay, this one we're going to look at thermodynamic and kinetic products. And the first thing that you always need to focus on is make sure you don't get into a rush, and you want to make sure that you draw the right compound. So here we're going to draw 4-methyl-penta-1,3-diene. And so the first thing I like to do is just go ahead and draw it out so I can see what I'm working with here. So there is our diene that we're going to use. So then the other actual next step is really to just, once you've got it drawn out, start looking and analyzing at all the different possible products. Can't spell possible, apparently. All right, so and the way that I kind of like to do this is I just pick one double bond, and I just start kind of reacting it there. So I'll pick the one here that is going to be closest to me here. And so if we react this with HBr, we're going to, of course, generate a carbocation. And I should note or point out that you could actually form this carbocation here, but notice that it is too far away and it's not allylic. So actually it's probably not going to form. So we want to look at the ones that are allylic. You probably have very minimal amounts of that, even though it is tertiary. So our other possibility is this secondary carbocation, and then of course if I draw the resonance structure, have this move over, then what I see is that I have another product that's primary and allylic. And then of course we have opportunity for bromine to go and attack the carbocation. And then all we got to do is draw our products. So here we have two possibilities. I'm looking now at these double bonds, and what I see is that my 1,2 adduct, and then I have my 1,4 adduct, and I can immediately see a difference in their level of substitution. The one on the left has two hydrogens that are on it, right, and the one on the right has alkyl groups that are on it there. So what this means is that this one is the more highly substituted double bond. And so this one is your Zaitsev product, and it is therefore also your thermo product for this case. Making this 1,2 adduct be your kinetic. Now, let's look at the other double bond. This is where it starts to get a little bit interesting. So we start by, of course, drawing this out. And then again, we're going to react it with HBr. Then I can move this through resonance. And then finally draw the actual final product here with the bromine coming in and attacking it, this bromide here. and we can look at our two products. So now what I can immediately see is that actually my 1,2 adduct, the one on the left here, actually is the more highly substituted double bond. So in this case, this 1,2 is actually both the kinetic product and the thermodynamic product. All right, so now we're going to do a synthesis, so next to last problem, and we're going to start from phenol. So the first thing you want to make sure you do is draw phenol. And then what I notice is that, first of all, the OH is a strong director and activates the ring towards electrophilic aromatic substitution and directs ortho and para. And usually para ends up sort of going first because of sterics, sort of preferred in that case. So what I'm going to do in this case is I notice that I've got to put two things on, or two separate things, three things in total. But what I need to do is put on the CH3 group here. And then I need two of these T-butyl groups. So in this case, what we're going to do, because of what I mentioned about para, we're going to add the methyl group first in the para position. So starting with phenol, all we need to do now is show what our reagents are. So add these guys in, and we will assume for the sake of argument that it only adds one time, and it puts it here in the para position. Then the next thing I need to do is I need to add two of these T-butyl groups. And so I've got the para position sort of effectively blocked now. And so I'm going to go ahead and add the bulky groups. And the OH in this case is still going to be my director. So it's going to want to go ortho and para even though it's bulky. And an easy way to add this is to treat an alkene like this with sulfuric acid. And this allows you to generate the carbocation that can then go to the go onto the ring there. So we need two of these guys, and so we see that once we add those in, we end up with our final product, which is BHT. All right, so the last question basically here was asking you which isomer is represented by So the key to this is which one of these is going to be conjugated, and that's the one I just circled. Notice that the double bond is in conjugation with the our ketone there, and so the one to the right is not conjugated. So the one that is in fact conjugated is going to sort of shift to a higher wavelength here. And remember that higher wavelength is lower in energy. And so then all we need to do now is just depict our transitions. So we have here the pi star, and then we have the non-bonding to pi star. All right, thanks for watching. I hope this helped.